So welcome on this pre-recording on graph traversals. So this lecture happens in the second half of lecture 3 in an 8-week summer course on computer algorithms. We start first with some definitions and terminology. What is a graph? So a graph consists of connected nodes. Some nodes actually may not be connected. A node in a graph, think about a map where the nodes are cities. Uh, a node is called a vertex, and we collect all the vertices in the set which we denote by the capital V. If two nodes are connected, then there is an edge, and we collect all edges in the set capital E. So a graph is a set of vertices and a set of edges. Here you see an example of a graph with 4 nodes, A, B, C, D, and with the corresponding edge list. So some nodes may contain cycles, may be connected to themselves. So the uh, node D is connected to itself. So we have the edge D, D sitting in there. We will be interested in deciding whether a graph is connected or not, whether for any two vertices there exists a path. A path is a sequence of successively adjacent vertices, a sequence of vertices where two consecutive vertices are connected by an edge. So in this graph, we see that there is the there is the path going from uh, B to D, which has to go via A. Okay, we have graphs which are by default undirected. We can also have directed graphs. In an undirected graph, which is the default, if we have a path, if we have an edge from A to B, we also have an edge from B to A. So from A to B and B to A, it doesn't really matter which vertex comes first in the pair in each edge. Therefore, we write AB only once and not BA. But in this second graph here, the second example, which is an example of a directed graph, now we draw the edges by arrows, and now the direction matters. You could say with an undirected graph, all the roads are bidirectional. With a directed graph, actually the default is that traffic goes only in one direction. Okay, directed, undirected. Another type of graph is the weighted graph. So we will have undirected, unweighted graphs, undirected, weighted graphs, directed graphs that are not weighted, directed graphs that are weighted. So we have 4 different types of graphs. Here is an example of a weighted undirected graph and a weighted directed graph. Now, how do we store the weights? We can store them in the edge with each edge. So there is now an extra element. So we give, when there is an edge, we add the weight as the third element in the edge that connects the two vertices. Paths are very important, also cycles are. A cycle is the path where the start vertex is the same as the end vertex. We also define for every vertex the degree. That's the number of edges that contain that vertex. The degree says something about the importance of a vertex, how well it is connected to other vertices. So in this example, in the undirected graph, B is connected only to A. So the degree of that vertex is only 1. A is connected to 3 vertices, so it has a higher degree. Okay, so that is the basic terminology. So before we go on to algorithms, let us first look to some very specific type of graphs, and these are the trees. The prerequisite for this course is a course on data structures, where trees also play a very important role. A tree is a graph, connected graph, without cycles. And by default, there is also an undirected graph. Um, so typically in computer science, the direction follows from the root down to the leaves. We draw in computer science trees upside down. Now the theorem that I will prove here gives an important characterization, or if you like, a property, but it's more than a property. So it doesn't take too much to see that if you have a tree on n nodes, that you can have no more than n minus 1 edges, and actually that you have exactly n minus 1 edges. So but the other way is also the other way also works. So that's why it's a characterization. If you have a connected graph and you have exactly as many edges as the number of nodes minus 1, then that graph must be a tree. So we will prove this. It's a proof by induction. So my motivation to show this proof is to again give another example of the technique of making proofs by induction. So one has to state that one does induction on what. So the critical number here is the number of nodes. One could also make the induction on the number of edges. That would work as well. The characterization is a two-way characterization, so it's two-way. So we go from left to right and from right to left. Typically, let's first do the easiest direction. If we have a tree is an undirected connected graph without cycles. We have to show that the graph is connected. That's already because we have a tree, so we don't have to show this, but we have to show that the graph has n minus 1 edges. So in the proof technique on induction, we have some steps to follow. So it's a technique similar like an algorithm. You have to initialize, you have a base case. For the base case, we are working induction on n, we consider a tree with 2 nodes, a root and 1 leaf. We have no cycles in a tree, so and it is connected, so we can have only one edge. One is n2 minus 1. Okay, base case done. Then in the second step in this technique, which is again an algorithm that you run, you must state what the assumption is. The assumption is that we just proven it for 2, we proven it for 3, we proven it for 4. We have proven it for all number of nodes with trees of k nodes, where k is strictly less than n minus 1 or less. And now we will have to prove it for a number of nodes k equals to n. So we go from trees with n minus 1 nodes or less to one larger tree. How do we do this? Well, we consider one extra node, and we have to connect it. So it has to be a tree. So we connect it by adding one extra edge. It's a tree, and that's the only thing we can do. We cannot add more edges, or we would start to create a cycle. If we are adding it typically to the leaves of that tree, if we would add the vertex to another leaf, then we would create a cycle. We may not do this. So we can make if we have a tree now with n nodes, then the only way that we can make that tree would be uh, having n minus 1 edges. And it is connected. Okay, the other way is a little bit harder. So to make this slide here self-contained, I put the definition of a tree again, an undirected connected graph without cycles. We work with n nodes. So we have a connected graph with n nodes and n minus 1 edges. We have to show that it is a tree. It is connected, so we omit that. So we have to show that with n minus 1 edges, we actually have no cycles. In the induction technique, the initialization, if you like, when you run that technique as an algorithm, is the base case. So we consider two nodes, n minus 1 edges, no cycle, so you can have only one edge. So it is a tree. That went quick. In the technique of induction, we state our assumption. So we have just proven the base case and all cases larger than that up to n minus 2 edges. So we know that any graph with number of edges n minus 2 or less is actually a tree. Now we consider a graph with n minus 1, and by induction hypothesis, the graph for which we have proven it has no cycles. So we kind of go from a graph with n minus 2 no edges or less to one with n minus 1 edges by adding one node and one edge. Okay, so the new edge and the new vertex, we only have one vertex that we can add and only one edge. That does not introduce a cycle. Because any cycle that we would introduce would actually contain that new vertex. But that vertex is only contained in one node, that new node. So another way of saying this with the terminology of degree of a vertex, in a cycle, every vertex has to have at least degree 2. So we didn't introduce a cycle. We have n minus 1 in making a graph with n minus edges. It is connected, therefore it is a tree. So this proves this characterization. Okay, we have proven a theorem. So that will be the main result, if you like, explicitly labeled as a theorem. But there will be other important properties that will not be stated as theorem, but that reduce to this property. Because we are going to compute trees in the algorithms that follow. Okay, there's one more thing that we need to do to get to the algorithms. And that's, if you like, is an alternative way to store graphs in a computer. via adjacency matrices. So an adjacency matrix is a square matrix of dimension the number of vertices, as many rows and as many columns as we have vertices. Here the vertices are called VI, Vj, but you can actually identify them by the unique integers 1 up to n, where the indices indicate the rows and the columns. So an adjacency matrix is a matrix of zeros and ones. There is a zero at the ijth spot if there is an edge, if there is no edge. If there is an edge, if there is a connection, then you have an edge. So you see that on the fourth row and the fourth column there is a 1 because D is connected to itself. There are two examples, a directed graph and an undirected graph. For the undirected graph, you see that the matrix is symmetric. So the top half is the same as the lower half. So that's one way on how you can save space already for an undirected graph. For the directed graph, you see that that symmetry no longer holds. It only holds for the AB and the BA, but then no longer for there's only one path from A to C, and but not from C to A. Oh, I'm sorry, there is one for C to A, so we have here a 1 on the third row, first column, but we don't have a 1 on the first row, third column. Okay. We had matrices of 0 and 1s for unweighted graphs. For weighted graphs, the 1s are going to be replaced by the weights. So we still have a 0 if there is no edge. If there is an edge, then we put the weight on the corresponding entry. So we see that there is a edge of weight 5 between A and B. Then on the second row, first column, we put a 5. First row, second column, we put a 5. Again, we have the symmetry for an undirected weighted graph. That symmetry may break down for a weighted directed graph, as you can observe on this slide. Okay, algorithms. So this is a course on algorithms. So far we have introduced a lot of terminology and a main property of a data structure, the tree. Let's now look at the problem that we would like to solve. We would like to decide whether graphs are connected. A graph is connected if for any two vertices in a graph there is a path. So the problem that we first consider is for any two vertices can we find a path from the first vertex to the second vertex. Okay, so how would we solve this? We could try to do this systematically by layering the set of vertices. So for the start vertex, U, we could look at all the neighbors of that vertex. These are all the vertices that are connected to the start vertex by an edge. So here you see the notation. So the first layer starting at U consists of all vertices V prime, so not the V. We exclude the U, so we don't want to go back to U. So if U would be connected to itself, it might end up in this first layer. And we actually don't want this. We don't want to store this. So we store all the neighbors. If one of these V primes equals V, then we are done. In our systematic investigation, whether U and V are connected via a path, we look now at all the neighbors to the neighbors of U. So we look at all the v primes, which are vertices, not u, not in the first layer. We don't go back, that are connected by an edge. An edge which starts in the first layer. So v double prime belongs to the first layer. And then we continue the neighbors of the neighbors of the neighbors. And here you see the general definition, which is an adaptation of the second layer. So we do not want to turn back. So this is a systematic search progressively going farther and farther from the vertex U. So we do consider only V primes that we haven't looked at before, and they are connected to V double primes connected in the edge list of the graph, and where V double prime belongs to the K-1 layer. Okay, I hope that with these definitions, so the first definition and the gate definition, by layering the uh, graph, the vertex set of a graph, we can actually decide whether there is a path from U to V. If our second vertex V belongs to some layer in the kth layer, then there is a path that consists of k edges. So if it belongs to the first layer, then it's directly connected. In the second layer, the path consists of two edges. Okay, so we've done this systematically. We've done actually much more. We computed a tree. And actually, the definition of the layers is the formalization of the breadth first search algorithm. So we are going to construct a tree, and it actually grows at the root, and actually it goes down. The breadth, the range of we're looking at what will become the children of the children. So the tree actually spans out. So the intuition for the name breadth first should be clear. Um, so the algorithm can now be stated in 3 steps. So with the input, we have our graph, we have what will become the root of our tree. A tree is any graph, so any graph we denote by a vertex set and an edge set. We have this V subscript T, E subscript T. So we start with the first layer, and the first layer is used to initialize the vertex set. We have the root, and then all the nodes that are in the first layer, and then also all the edges that start at U and that end at the vertex in that first layer. If there are no neighbors of U, then we actually are already done. Otherwise, we are computing the second layer. We will have a counter K, which will count the layers and actually counts the distance, if you like, from the vertex U. So you see the formula to compute the kth layer. We don't go back to U. We don't go back to any previous vertex in a previous layer. We collect all V primes that are connected to a V double prime at the previous layer. So the mathematical notation is recycling the definitions, but it is also at the same time very precise. The algorithm stops when one of the layers becomes empty, and you can already think, will it ever stop? But if we go to the third step, we update the vertex set V subscript T, adding all the nodes at the new layer, and also updating all the edges that connect the um, the V prime from the current layer to a V double prime in the previous layer. And we continue this. So there is a we go to step 2 as long as the sets are not empty. Okay, is this an algorithm? An algorithm, as we defined it in the very first lecture, the very first definition, is an unambiguous, ordered set of executable steps. So we do computer algorithms, and any algorithm must terminate. So I hope that by the mathematical definitions I have shown that there is no ambiguity here. Everything is clear at this point. Also that it is executable. We will see examples of that in a minute. But first, before we compute an example, we have to make sure that will it actually be terminate? Well, yes. So it terminates because we are layering the vertices. And it's important that we never look back. So we don't go back to U, we don't go back to any of the previous layers. So another way of seeing this, that in the computation of the layers, what we subtract from V, so the candidates for V prime, they actually become smaller and smaller. We have fewer and fewer V primes to consider. So the algorithm must stop if the vertex set is finite. So, and in this course, we actually don't consider infinite graphs. So the proof of correctness goes via by contradiction. If the algorithm does not stop, well, then the vertex set must be infinite. Okay, the bottom line question is, why is it a tree? It's not because we say that it is a tree that it is a tree. Well, what is a tree again? It's an undirected, connected graph without cycles. We don't cycle back. That's already one thing, and all the layers are connected to each other. That's one way to show this by using the definition. You could also use the characterization. So observe in step 3, when we update the vertex set and when we update the edge set, what is actually common is the layer K. So we add as many edges as we have V primes from the kth layer, and the kth layer gets added. So we have only one time, only at the initialization, where we add one more vertex, and that's the root. So we have exactly n minus 1 uh, edges, where n is the number of nodes. Okay, good. Um, so I know that I've spent quite some time on this formalization, that at this point for it, but if you look at this formal notation, it may be very intimidating. So that's why an example is actually very good. So here's a graph. So you could consider this as a map. And we would like to visit every vertex very systematically. So you see, if we start at 0, there are 3 possibilities where to go. Well, in the breadth first search, we consider all 3 of them. Okay, so that's the first step. We will visit 1, 3, and 4. In the next step, actually, we now have to look at the neighbors of the neighbors. We will visit from 1, so it's good that we have an order on the vertices. We will start by looking at the neighbors of 1, excluding 0, so we don't look back. And the degree of 1 is 3, so we have 2 other possibilities, so this is 5 and 6. In the next step, in looking at the neighbors of the neighbors, we look at 3. So 3 is connected to 2 and to 8. So we visit 2 and 8. Okay, we are left with 4, so 4 is directly connected. Um, but now notice that 4 is connected, so 4 is connected to 0, we don't turn back. It's connected to 5, but we have already visited 5 from vertex 1. Actually, we have also visited 6 from vertex 1. So this is where the set minuses in that notation was so important. So we will not visit 5. If we are at 4, we will not visit 6 again. There's only one possibility, and that is 7. Okay, at 4, we visit 7. And if we look at this, it depends on how you tilt your head a little bit. You can actually recognize that the graph on the right is a tree. So we have visited each and every vertex. So you can see that we visited 7 as the last one. 8 was visited when we, 8 is visited when we visited 3, I'm sorry. Okay, so the next picture makes it clearer. So the result of this breadth first search algorithm is the breadth first tree. So again, is this well defined? Well, we have a well defined algorithm. So you could say that the breadth first tree is the output of an algorithm. Okay, that's our first result. Um, the problem with this a little bit is that here it looked very deterministic, but in some sense, the mathematical notation with the v primes did actually not specify the order in which the vertices should be visited. If you order, if you have a unique labeling of the vertices, which you always have, then the algorithm becomes very straightforward. But there's actually, from starting from 0, there's actually no direct way to decide should you first visit 1, 3, or 4. Doesn't really matter to this algorithm. In practice, it does matter. Okay, so before we go to the other algorithm, one more definition. So with this algorithm, you can compute what is called the connected component of the graph that contains U. So it's denoted by R. It contains the reachable vertices, those vertices that can be reached from starting at vertex U. So in here, that connected component is formally defined as all the um, edges that are all the edges. So it's actually the subgraph. So it's not, I'm sorry that I was confused a little bit. So the vertices are the same, but you kind of add in all the edges again. So if the graph is connected, then the connected component of G containing U is just the graph again. So this definition makes most sense if you want to count the number of connected components in a graph. And you can do this by running this algorithm until you have no more vertices that don't belong to a connected component. Okay, so breadth first search is one search pattern, and in some cases this might be what you need, but in other situations it might not be, um, and that's why we introduce the depth first search. The problem in which the depth first search is most applied is the problem of finding the exit in a maze. You find you somewhere in a building and you want to get out as quickly as possible. You're not going to do the breadth first search. You're going to go systematically in one direction, looking for going as far as possible from your origin. But it is the same problem that we solved as before. So given two vertices, is there a path from U to V? Okay, and this is done by what is called a depth first search. And depth first, we're going to compute the tree as well. And since the trees in computer science are drawn upside down, it's like that we go deeper and deeper into that tree. So it's formulated recursively. So what I will be needing will be the edge set, E. We start at U, so the second argument of that algorithm is U prime. So U prime is the name of a formal parameter. So it is U at the start, but it would be wrong to keep on working with U. So U prime changes. U prime becomes a neighbor of U um, at the time when you make the next call to the algorithm. So we are going to compute a tree as well, which will be called the depth first tree. So the tree is computed as a vertex set and an edge set. So these are, if you like, the output parameters. So you call this algorithm with zero sets and they are updated. So we start by visiting U prime. So we add it to the vertex set. And then for each neighbor of U prime, when there is an edge, U prime, V prime, for some V prime, when we haven't visited before, then we will add the edge and we will visit V prime. Okay, recursion is a very powerful technique. So in some sense, this is um, also a prototype algorithm for enumerating all possibilities. So in the previous lecture, we mentioned brute force algorithms. Well, brute force algorithms can be implemented in this way. Okay, why does this terminate? Same argument as with the previous. Um, the set here, so you consider all the edges, but you can see that the vertex set for your tree only grows, and you consider newer V primes. So the V primes that you will visit will not have been visited before. So if the algorithm would not terminate, then your vertex set would be infinite. So you would always have new vertices to visit. Um, and that cannot be. So the recursive call must stop at some time. Okay, so why is it now a tree? And now it's probably useful again to think about the characterization. You can see that each time when we update, so we have u prime and v prime, we update the the vertex set, and also we update the edge set. So for every update of the vertex set, there is an update of the edge set. So this is why you have this n minus 1 again. And it is connected. Um, so again, so if you're interested in the original problem, um, if you're not interested in the depth first search tree, then actually you can stop as soon as you find a v prime that equals the v. As soon as you have found the exit, you terminate. That is an optimization or a small modification here. We say that the algorithm is a backtracking algorithm. So when you are done executing the if statement, then you go to the next edge. So we backtrack, and when this ends, so it's here very instructive to actually write down the tree of function calls. Okay, so let's look at an example. We use the same um, example again, 9 nodes starting at vertex 1. We go from 1 to 0, from 0 to 1, starting at 0, from 0 to 1. 1 is connected to 5 and 6, so we pick 5 because that's the first one. From 5, 5 is connected to 2 and 3, so we go to 2. 5 is actually also connected, of course, to 1, but we don't go back. So keeping track of the visited nodes, we are sure that we don't turn back. At 2, we go to 3. From 3, we have 3 choices because the degree of the vertex is 3. Well, but we have only one choice, and actually we can't go back to 2, but we can go to 8. From 8, we can go to 5, but 5 is already written down. We can go to 3, but we don't turn back. Therefore, we go to 7. From 7, we go to 4, and so in some sense, this is a little bit confusing because I haven't, so perhaps I should show it like this now. Because the original network was not there anymore. So 4 is connected to 6, 7, and 5, but actually 5 and 5 we already visited, and we come from 7, so 6 is the only possibility. Okay, and after that, so 6 is connected to 1, but we visited 1 already, and we come from 4. So there the algorithm terminates. And we end up with essentially only one branch. So it is a tree. And it is the depth first tree of the graph. Okay, so what do we observe? Well, we observe that the result is significantly different. So here is the result of the depth first search. And it depends, of course, what you want. If you want to quickly find the exit in a maze, then depth first search tree will be what you will be needing. But that tends to be very narrow. In the extreme case, just one branch. If you want short paths, route to leave, then actually the breadth first search tree is preferable. We may come back to that later. Now, both algorithms produce trees, and both algorithms will actually can detect whether a graph is connected or not, and actually produce also all connected components. Okay, I will end with a question and an exercise essentially. When are the trees the same? And I can give you already the hint. If the graph is already a tree, then there's only one possible outcome. Now, the question for you now is so you can write that down. That already gives you credit for the exercise. But the the next thing there is actually to show that this is indeed the case, because there's only one unique in both outcome. But is that the only situation? It's and you can show this with an example. You can show a very simple example of a graph that is not a tree and for which you have different uh, trees. Okay, there will be homework. So here is the homework. I hope that the lectures are clear enough to get you started on the exercises.